Good morning, my dear students. So today in this sessions we are going to learn regarding the basic steps of finite element analysis. Basic steps of finite element analysis. Okay, so in order to find the solution of any complex problem, we can easily solve by the finite element method. But the some of the basic steps we need to follow. So from that one we can easily solve any type of the field problem like structural problem, heat transfer problem, as well as we can easily solve the fluid problem, or we can say as we can easily solve the CFD problem. We can easily solve with the help of finite element method. Okay, but after the design is completed, we need to analyze on them. So the analyzing steps are almost similar except slight modifications. So for example, the general steps we need to adopt for analyzing the any type of the structural engineering problem. The first step is discretizations of structure, and second steps is selection of displacement function, and third steps is derivations of elemental stiffness matrix, and fourth step is assembly of algebraic equation for the overall discretization of continuum, and fifth steps is applying the boundary condition, and step 6 is to find the unknown value with the help of finite element method, or we can say as finite element analysis method. So we are going to discuss one by one. Okay, the first thing is, in order to find the solution of any complex problem like we can say as continuum problem by the finite element method, is it right? So with the help of finite element method we can easily solve the any type of the field problem like structural problem, heat transfer problem, as well as fluid problem. We can easily solve with the help of finite element analysis problem. Is it right? In order to find in order to find the solution, for a complex problem, by the finite element method. F, it is represented by F dot M. Okay dear, and the some basic steps we need to follow to solve the any type of the field problem like structural problem, heat transfer problem, and fluid flow problem. Is it right? Some basic steps are we need to follow. Is it right? So some basic steps are followed. Whatever be the field of problem, any type of the field problem we can easily solve with the help of finite element analysis method. Is it right? The whatever be the field or problem like structural problem, heat transfer problem, and fluid flow problem. Okay, and so if you want to analyzing steps are almost similar, except we need to do the slight modifications. Is it right? So the analyzing steps are almost, is it right, almost similar, except slight modification. For example, the first one is, we can say as discretions of the structure. The general steps we need to adopt for analyzing a structural engineering problem, we need to discuss one by one. General steps adopted for analyzing the general steps we need to adapt for the analyzing a structural engineering problem are discussed. The first step number 1. So what is the first step here? Discretizations of structure. So what is the meaning of discretizations? The discretization nothing but we need to divide the whole complex structure into the smaller part, we can say as discretizations. Is it right? So what is the first step? Discretizations of the structure. Discretizations of the structure. Okay. So the first steps in the finite element method is, the first of all we need to divide the whole complex structure into the smaller part. Is it right? Let us see. This is my rectangular object. Okay, so this rectangular object we are divided into the smaller part. So the divide the whole complex structure, this whole complex structure into the smaller part. The smaller part, what we can say here, we can say as subdomain. What we can say? Subdomain. Is it right? So if divide the whole complex structure, what we can say here, we can say as discretize. What we can say? Discretize. This is the whole body. It is looking like, how is it? It is looking like a rectangular lamina. So if you divide or discretize the whole complex structure into the smaller part, This is the smaller part, is it right? Like this, the horizontal and vertical, like this. If you divide the whole complex structure into the smaller part, is it right? So what we can say here, we can say as element. Let us see. So here to here one node, here to here second node. If we joining the first node to the second node, the forming of element we can say as the first element. If we joining the second node to the third node, the forming of element is E2. If we joining the node from 3 to 4, this is the fourth node. The in between the lies the element is we can say as E3. If we join the node from 4 to 5, it's 4 to 5, the element is lies is E4. If you're joining the 5 to 6 node, the forming of element is E5. So you understood that here how many nodes are there? Total node is 6. How many elements are there? It should be lesser than node. Here node is, how much is there? Node is here 6. How much element is there here? 5. Is it right? If you are joining the entities from the first element to the second element, the forming of element is E1. If you are joining the entities from the 2 to 3, the forming of element E2. If they joining the element from joining the node from 3 to 4, the forming of element is E3. If they are joining the node from 4 to 5, the forming of element is E4. If you are joining the node from the 5 to 6, the forming of element is E6. Like this is there. You need to follow the like 7, 8 node, 9, 10, 11, 12, like this. Is it right? We need to follow. So the first step in the finite element method is, first of all we need to divide, or we can say as discretize the whole complex structure into the smaller region, into the smaller part. Is it right? The smaller part, what we can say here, subdomain. So we can say as finite element by line or surface, we can say. So always you know very well, this interconnected element may have the different shape and size. Let us see over here. So this is my geometrical model. What we can say here? So geometrical elements. So here the load P1 is acting here in between, and the load P2 is acting in this lines. So this structure, what we can say here, we can say as the geometrical model. Okay, the direction is in here. So let us see, if you want to describe the model, how's it? So this geometrical model I am converted into the described model. Let's see over here. So first thing is I am cut up to here like this portion I am making as a stub bar. This is my center point, this is origin axis. Okay, and here again I am reducing up to from here like this. Let us see. So here this is the first node, and this is the second node, and this is the third node, and this one is the fourth node, this one is fifth node, and this is sixth node, and this one what we can say, seventh node. So the first node is interconnected. So first node is connected to the second node. The forming of element, what we can say, element E1. What we can say here, element E1. If you join the node from second to third, the forming of element is E2. The joining the node from the 3 to 4, the forming of element is E3. The joining the node from 4 to 5, the forming of element is E4. The joining the node from E to 5, the forming of element is E5. If joining the node from the 6 to 7, the forming of the element is E6. Is it right, Nadia? Okay. So the first steps in the finite element to divide the given body into the smaller region is called as, what we can say here, we can say as element. What we can say here, element. So the analysis is carried out of each point the analysis is carried out each of this element, the point where the property are to determine for the elements, what we can say as the node, or the joining of the node from the first entity to the second entities we can say as the element. Okay, if it is carried out the point, we can say as the node. Is it right here? So I am representing the first point. The first step, it's visible. Okay, the first step in the finite element method is to divide given continuum, what we can say continuum, nothing but we can say as body, into the smaller region. Is it right? Region. So what we can say here, we can say as element. Region is called as elements. Is it right? Then analysis is carried out for each of these elements, the point where the property are to determine for an element, what we can say as nodes. Is it right? The analysis is carried out for each of these element, the point where property are to determine, the points where the properties are to be determined for an element, so what we can say here, or called as, we can say as nodes. Okay dear, so let us see over here. I am considering one 2-dimension lamina. So what I am doing here, I am divided into the half region. Is it right? Again I am divided into the smaller part. Okay, again I am joining the point from the first, this point to the above point, like this. Okay, so here if you observe from this figure, what they forming here, they forming of triangular element. What are they forming here? They forming of triangular element. Is it right? So take this snapshot here. Okay, I will write here. Okay, so as shown in the figure, this is a discretizations of a structure member. So the element taken is a 2-dimension element. How is it dear? It is a 2-dimension figure of a 2D triangular element. This triangular element having how many nodes here? First node, second node and third node, and each node they having the 2 degree of freedom. How? Let us see over here. If I am taking this triangular element, in the x and y direction. This is the x direction and this is y direction. This x direction, what we can say is here displacement u, and the y it is represented by v. So I am taking this triangle element, first node, second node and third node. If we join the node from the first node to the second node to the third node, third to the first node. So this is first node, second node and third node. Here if you observe here, how many nodes are there? Total 3 nodes. How many degree of freedoms are there? Total 6 degree of freedom. Let us see over here. First one is u1, v1. This is u2, v2, u3, v3. Here how many nodes are there? 3 nodes and 6 degree of freedom. u1, v1, u2, v2, u3, v3. So total how much? 6 degree of freedoms are there. Is it right? So let us see over here. Discretize body as shown in a figure. The element we are taking is a 2 dimensions element, that is 2D triangular element. How is it here? It is a 2D triangular element. This triangular element having the 3 node and they having the total 6 degree of freedom. How many degree of freedom here? 6 degree of freedom. And each node they having the how many degree of freedom? Each node on the first node 2 degree of freedom, on second node 2 degree of freedom, on third node 2 degree of freedom. Total how many degree of freedom here? Total 6 degree of freedom. On each node 2 degree of freedom. Is it right? The triangular element having how many nodes? 3 nodes. First, second, third. 3 nodes and each node there are how many, sir? There are 2 degree of freedom. Each node they are having the 2 degree of freedom. Total how much? 6 degree of freedom. Each node there are 2 degree of freedom in x direction as well as in the y displacement. In x displacement and y displacement. So this element, this triangle element shows the how many degree total? 6 degree of freedom this shows. The triangular shown there are 6 degree of freedom. Okay. Second steps. The second step is selections of the displacement function. So what is the second step here? Selection of the displacement function. Selection of the displacement function. Second step is selection of displacement function. So it is generally not possible to select the displacement function that can represent the actual variations of displacement in each element. Is it right? So generally we know very well, hence the basic approximation of the finite element method is introduced at this age. So there are three interrelated factors which influence the selection of displacement model. The first condition is that types and degree of displacement model must be chosen. For example, let us see this figure. This is how it is a one dimension, or we can say as two-dimension element. What we can say here? Two-dimension element. So here, if you consider this is first node, second node, third node, and this is the fourth node. So type is how is it here? It is a type. We have to know about it. It is a 2D bar element. We can say as it is a 2D bar element type. And degree of displacement model, here it is a degree of displacement model is u1 v1 u2 v2 u3 v3 u4 v4, like this. Is it right? First of all, we have to know about what is that type and what is the degree of displacement model must be we need to choose in the where in the displacement model. And the second step is the particular displacement magnitude that describe the model must be selected. Is it right? The first of all, we need to select any particular model that this particular model displacement magnitude describe the model must be we have to select. And third thing is the displacement model must specify the certain requirement which ensure that the numerical result approach the correct solution. So if you are following the some type of some type of this displacement model, they not give the specify certain requirement. Is it right? So we need to ensure that whatever the model we are selecting, the must specify the certain requirement which ensure that the numerical result that approach the correct solutions. Is it right? As well as let us see. So this one delta 1 and theta 1 we can say as displacement matrix, and y1 and m1 is represent the force matrix. So the displacement and the force matrix we can corresponding the nodes and element, so we can represent in this form. The displacement matrix we can represent as delta 1 theta 1 delta 2 theta 2 delta 1 theta 1 delta 2 theta 2. And the force matrix, which type of the force is acting on the each element. It may be tensile force, it may be compressive force, it may be bending force, it may be twisting force. We can easily analyze with the help of the force matrix method. And the force F we can represent by y1. So this is y1 m1 m1, and this is y2 m2. Is it right? And the third steps is derivations of elemental stiffness matrix. Take this snapshot here. Okay. Step number 3. Derivations of elemental stiffness matrix. Derivations of elemental stiffness matrix. Okay, so we know very well from this equilibrium equation for any element is determined by using of principle of minimum potential energy. Equation is stated by Ku equal to F. The K is indicate that it is an element stiffness matrix, and U is represent the nodal displacement and F is represent the nodal force matrix. So this method we need to adopt in the problem. Is it right? Equilibrium equation, okay, it's visible. Okay, equilibrium equation for an element is determined by using the principle of minimum potential energy, and the equation is stated as K U equal to F. So we know very well, so the K is represent the elemental stiffness matrix. What they represent here? K is represent the elemental stiffness matrix and U is represent the nodal displacement matrix and F is represent the nodal force. So this equilibrium equation for an element is determined by using of principle of minimum potential energy, and this equation is stated in this way: Ku equal to F. So the K is represent the element stiffness matrix and U is represent the nodal displacement and F is represent the nodal force. Okay dear? And then the next step is assembly of algebraic equation for the overall discretized of continuum. Step number 4. Assembly of algebraic equation for the overall discretized continuum. Okay. So in this method, the some steps we need to follow in determine the global stiffness matrix, or we can say as overall stiffness matrix, and global force vector and overall force vector. So this equilibrium equation for the entire continuum we can easily represent by Ku equal to F. Is it right? Ku equal to same equation we can represent here. So we know very well these steps involve in determine the global stiffness matrix and global force vector and overall force vector. This step involved these steps involved in determining the global stiffness matrix, global stiffness matrix and nodal displacement and global force vector and global force vector. Okay, so this equilibrium equation for the entire continuum, so continuum nothing but body, is it right? The equilibrium equation for the entire continuum, so what we can represent here, we can represent as same equation, ku equal to f, ku equal to f's. So what the k is represent, this k is represent as global stiffness matrix. What they represent here, global stiffness matrix, and u is represent the nodal displacement, like k, u is nothing but u1 u2 u3 u4 like this, and f is indicate that global force vector like f1 f2 f3 f4 f5 f6 like this, is it right? So f is indicate that it is a global force vector. Okay dear, and step number 5 is applying the boundary condition. There are three methods we need to apply the boundary condition in the finite element method. Is the first method is elimination method, second one is penalty method, and third one is multi constraint method. So almost all we are going to follow the two method only, one is the elimination method and another one is the penalty method. Almost all we are using these two method only, is it right? Step number 5, applying boundary condition, there are three methods of applying the boundary condition in the finite element method. Is first one is elimination method, second one is penalty method, third one is multi constraint method. There are three methods of applying boundary condition in finite element method. The first one is elimination method. We need to cancel these terms, okay, so we can say as elimination method, is it right? So this elimination method you can easily understand in the problem, is it right? And second one is penalty method. Penalty method is most important here. And third one is multi constraint method. Multi constraint method. And second one is to find the unknown. So these steps involve the finding the unknown such as displacement as well as stress and strain. We can easily solve with the help of unknown methods. Next one is step number 6. Step number 6, to find unknown. Okay dear, so in this method the sum of these steps is involving to finding the unknown such as displacement and stress, strain, is it right? These steps involve to find unknown such as displacement, stress and strain. Okay, I hope so no one is having the doubt regarding this class. In the next class we are going to learn regarding these types of elements we are going to learn. If you have any doubt regarding these sessions, please write down in the comment box and don't forget to subscribe my channel. Thank you.